Hello guys, good evening. ACM Student Chapter of University of Moratuwa presents webinar series on network concept security. So this is the third session and session will be conducted by Chamika Sudusinghe. Chamika is a third year undergraduate of the Department of Computer Science and Engineering. So, good evening Chamika. Chamika, good evening. Hello, Chamika. Can you hear me? Guys, sorry for the technical issues. So please wait.
Hello.
Good evening. Good evening, Chamika. Yeah.
Yeah. I can hear you now. So previously there was an issue with my microphone, I think. Microphone as well as the speaker, so I was not able to hear you. Sorry for the inconvenience.
Okay, yeah. You can start the session when you are ready, yeah.
Yeah, sure. I'll start the session. So okay. So good evening, everyone. So hope you're doing well. And I just wanted to know, like, before I start the session, whether like there are any one like who have not been for the previous two sessions. So if you have not been to the previous two sessions, can you just like mention that in the chat? So I'll be able to give you a brief overview before I start. So this means like everyone has been for the previous two sessions, or this is the first time that anyone is joining? So anyway, I'll briefly touch on what I have discussed before. So let's move on. Yeah. So I was talking about system on chip, network on chip, and the communication pathways on system on chip. So system on chip is basically an integrated chip which contains system on chips are like integrated chips that can contain inside a single silicon chip. So it's we can find system on chips in the heart of computing devices, from simple IoT devices till complex navigation systems in airplanes. So system on chips are like in contrast to the common traditional motherboard based PC architecture, where like in motherboards we are having a central interface in circuit board which houses and connects detachable components and replaceable components. But system on chips integrate all these components into one single integrated circuit, as if all the functions were built into the motherboard itself. So Apple A12 Bionic chip is an example for a system on chip, as well as we can find system on chips in Raspberry Pi as well. So in terms of definition, a system on chip combines the required electronic circuits of various computing components into one single integrated chip. So that's the definition. So in terms of another definition that we have talked about, it is the IP core. So IP core is the intellectual property core. It is a reusable unit that is developed with the idea of licensing to multiple vendors for using as a building block of different system on chip design. So like the image that shows you is a system on chip, and there are like GPUs, memory, CPU, DSP, connectivity modules, and others. So each one of these is an IP core. So it's like a small component inside a system on chip. So these are designed by various vendors and built at the same time in somewhere. So the third one is about the on-chip communication. So due to the complexity of the system on chips, there should be a communication method which can communicate with a lots of number of IP cores. So the proposed mechanism was network on chip, which we discussed in the last lecture. So network on chip architecture is widely used to interconnect intellectual property cores and the system on chip designs, and it uses a packet based communication approach. So it has allowed like the computer architects to fully utilize the computational power of system on chips and facilitating low latency and higher throughput. So apart from the other communication methods that we discussed previously, like point-to-point architecture, bus architecture, uh, network on chip architecture is considered as an aggressive long-term approach for on-chip communication because it can deal well with the design issues of communication performance, power consumption, signal integrity, and system scalability. So those were the pretty basic ideas that we discussed in the previous two sessions. So this is an illustrative example of system on chip with network on chip based communication to interact with third party intellectual properties that are inside. So you can have an idea like different FPGAs, controllers, GPUs, analog to digital converters, digital to analog converters, input output processors, memories, all are connected using a network on chip. So the connections and the communications can be done properly when the number of IP cores increases as well. So as we've discussed about the topologies and the architecture of network on chip as well as system on chips in the previous two sessions, today I'm going to talk about the security side of it. So just to give you an idea about the security, like there's a like growing interest in the industry to use the network on chip to secure the system on chip because it's evident like there are like components called network on chip locks, flex, network on chip resilience package, and various other things as well. So the key points about the security is like the network on chip has access to all the system data inside the system on chip, and as well network on chip spans across the entire system on chip, as you can see here. And the network on chip elements are repetitive in a way that the modifications can be replicated, easily replicatable. So if you thought about how the communication is happening in a network on chip in the previous webinar where we discussed about XY routing, you know how the components inside a network on chip is used for the communication performance as well. So the basic idea is like a compromised network on chip intellectual property can corrupt data, degrade performance, or even like steal sensitive information from there as well. So now you have a good idea like why do we need like security for network on chip. So if we consider like there might be two use cases, like there might be an instance like the network on chip itself can be corrupted, like it can be malicious as well as it can provide the other things, like it can provide the path for the other malicious implants to communicate with each other and put forward like various malicious messages in the system and maybe degrading performance at the end. So this is why we need network on chip security. So as I discussed earlier, like system on chip complexity and the tight time to market constraint deadlines have shifted the in-house system on chip manufacturing process to a global supply chain. So I discussed about this in the first webinar. So system on chip manufacturers outsource parts of this manufacturing process to third-party intellectual property vendors. So global distribution of mechanism of this design, validation, and fabrication of intellectual properties can lead to different and various security vulnerabilities, and these adversaries have the ability to implant malicious hardware, software components inside these IPs. So the most popular forms of vulnerabilities that we can find now, the first one is the malicious implants. The second one is the backdoor using test debug interfaces, and the third one is the unintentional vulnerabilities. So if we talk about the malicious implants, an adversary can utilize the malicious implants, which we call hardware trojans. You'll hear this term in the next slides, because hardware trojans is the word that we are going to use for malicious implants, and they cause malfunctions or facilitate information leakage or maybe like corrupt the entire system at the time. So that's what hardware trojans do. The second one is the backdoor using test debug interfaces. So an adversary can also exploit the legitimate test and debug interfaces as a backdoor for information leakage. So many security vulnerabilities can lead to this as well. So the final and the third method is the unintentional vulnerabilities, because like when creating a complex system from the design perspective, there can be like several instances that there are unintentional vulnerabilities caused by design automation, computer-aided design, so by mistakes of the designers as well. So these vulnerabilities can also lead to untrusted intellectual properties as well. So if you talk about like the attacks based on these malicious implants, such as hardware trojans that I explained, this rely on the being integrated to the system on chip without being detected at the post silicon verification state during the runtime. Like, so it is more likely that the hardware trojans are inside the IP cores of the system on chip, so they cannot be like detected previously in the specification document as well. Like they can be inserted into the design in several places, such as by an untrusted CAD tool or designer, or at the foundry via reverse engineering. So even if all the intellectual properties are tested before integrating, hardware trojans can still go undetected because of the complexity of the design with billions of transistors, which make physical inspection or 100% coverage in design verification or validation cost a costly or an impossible process to execute. So furthermore, like if I had to explain about this Trojan can mask their behavior as transient errors, and as well as like they can be activated only when a specific condition or a combination of conditions are satisfied. Like a smart attacker would like carefully craft these Trojans activation method so that it become really difficult for someone to detect. Like, so if there are like 15 or 16 activities that can happen inside a system on chip, uh, specific to an IP core, let's say like there are like A to Z activities that can happen, but only if A, C, and E activities happen simultaneously, these malicious implants, which are called hardware Trojans, will be activated. So, like there are like many permutations that we can consider about how these activities are happening, and it is really difficult to test and debug to find these as well. So the the use of these third-party network on chip IPs has grown rapidly over the years. So this is mainly due to the increase of the complexity of the design, and there are like several companies in the world, like they have developed like several types of network on chips, maybe like flex network on chip, where there are like they are to like hardwarely find if they're an attack as well. So therefore like there's a simple opportunity for the adversaries to attack the system on chip through malicious implants in network on chip intellectual properties as well. So I believe like you got an idea about the security issues that can happen inside a network on chip. So then I'll move on to like what are the challenges that we find in network on chip security. The first one is about the conflicting requirements. So while enabling communication between intellectual properties, network on chips need to satisfy a wide variety of requirements, including security, privacy, energy efficiency, domain-specific requirements, and real-time constraints are some of the things that it has to satisfy. So it is really difficult to satisfy conflicting requirements such as like security and energy efficiency at the same time. So for an example, it may not be possible to implement traditional security measures such as encrypting text with security ciphers, or like using hash functions such as in IoT devices. So like security and domain specific requirements in a network on chip might not be compatible as well. So like in an example, in an automotive network, when a potential security breach is detected, pausing all systems to check the malfunction is not an option, because if you consider a car which is moving and going at a certain speed, if a malfunction happens, we cannot like stop it at the same moment that it happens, because like it can abruptly cause catastrophic consequences because of that. So there need to be an innovative solutions to secure the network on chips with like lightweight security mechanisms and customized for like different domains as well. So the second point that I have to address is the increased complexity. So the complexity of the system on chip designs have made exhaustive security validation an impossible task, because like most of these intellectual properties come as black boxes from various vendors in the world, and they do not reveal the design details in order to maintain the competitive market uh, advantage for them in the market. So like if you consider like if there's a network on chip, system on chip with 100 IPs, and if 50 IPs are given by 50 vendors, there are like 50 instances, like we do not know how those 50 components are designed and what are the aspects of them. So it is like really hard for the engineers for verify these components. So the modern verification tools which try to detect these erroneous functionality, whereas like security functionality and verification functionality might be really complex. And as I mentioned before, like these erroneous situations get triggered only in certain specific set of inputs. So it might be really hard because due to the increased complexity of network on chip. So therefore, like using security validation tools during design time to capture all the security vulnerabilities that can happen might not be the best case scenario. The third point that I have to discuss is the diverse technologies that are happening inside a system on chips as well as network on chips. So we've discussed about that in the previous webinar as well. So the electrical network on chip is the go-to design that we have. Like, but in these days, like there are like options that we can consider about the optical network on chip as well as the wireless network on chip as well. So the security solutions for the network on chip in the electrical network on chip, which are based on the electrical wiring, might not be a direct fit for the optical network on chip as well as for the wireless network on chip. So we might have to consider a different topology in terms of these other network on chips, and the difference of these technologies might cause it is really difficult for the engineers to verify that these network on chips are performing as they are expected to perform. So now we have an idea about what are the issues that can happen in network on chips and what are the challenges that we have to face and why we should do it. So then we have an idea about that this is something that is happening inside, and these are few of the security attacks, maybe like the types of security attacks that can happen inside a network on chip. So one is called eavesdropping attack, the other one is called spoofing or like data integrity, the third one is the denial of service, the fourth one is the buffer overflow, memory extraction, and the fifth one is the side channel attack. So today my main focus is to give you an idea about what are these attacks and how these attacks are happening and what are the threat models that these attacks are using. So this is like these names might be new for you all, but what you have to understand is like this is, even though like this is regarding on-chip communication, these attacks are happening in the computer network environment as well. So the concept behind these attacks are similar in both network on chip environment as well as in the computer network environment as well. So what you learn or get to know here about these attacks are applicable for the computer network environment, but the only difference might be like we have like separate set of layers in the computer network environment for different purposes, and the implementation might be different, but the basic idea behind these attacks are the same. So getting an idea about these attacks might be useful for you if you're interested in network on chip as well as in computer security as well. So it can be applied in both cases. So the first one is called the eavesdropping attack. So it's about listening to confidential information that passes through a network on chip when the other intellectual properties are communicating. So if we say like, if you can remember last time, if we consider a mesh network on chip topology, so if we are sending a message from like first intellectual property to fifth intellectual property, when the transmission is happening, IP and IP in the middle, maybe the number 3 can intercept that message and send it to a completely different intellectual property, maybe 12. So that is an example for a eavesdropping attack. It's about like, if I have to explain again, it's about listening secretly to a message that is passing through. So the second one is the spoofing or data integrity attack. So it is like intentional data corruption to cause erroneous behavior or system failure, whereas a spoofing is an impersonation type of attack that disguises the communication from an untrusted IP as well as from a trusted IP. So the spoofing or data integrity attack is like simply like if I am A and if some of you are B, so A and B are communicating, and there's someone called C who is impersonating A and pretend that C is A and try to connect with B. So that's basically what is a spoofing attack is. The third one is the denial of service attack. So denial of service attacks are the attacks that overwhelm the network resources in an attempt to cause performance degradation, real-time guarantee violations, and reduction of battery lifetime as well. So one of the instances in denial of service is flooding the network. Like, so if I have to explain it again, like in denial of service, what happens is like in simply if some communication is happening within an environment, suddenly the number of the rate of communication increases suddenly due to some of the IPs sending lots of messages at once, and the entire system get jammed because of that. So that's a denial of service attack. So that's simply the explanation. So the fourth one is the buffer overflow attack or memory extraction attack. So it's like gaining access to unauthorized privileges, levels, and memory locations. So that's more likely about buffers. And if you are familiar about the stacks in the memory, so it will give you an example. I'll give an example later. So the fifth one is the side channel attack. So side channel attacks mount attacks by utilizing the non-functional properties such as time, power, and electromagnetic radiation as of the measures to attack this network on chip. So these are the 5 types of attacks which can happen in network on chip as well as in computer network environment. So if you're not familiar with these attacks, do not worry. Like if this is the first time you're hearing it, so it's good to know about these attacks, because like even in both cases, like in computer networks as well as in network on chip as well. So there are like in everyday like there are like new malicious implants and new types of these attacks. These attacks can be segmented into subtypes as well. So there are like instances that there's a new type of attack is coming and emerging, and the security side of these, how to detect these attacks is vital for both systems as well. So for both network on chips and computer networks as well. So knowing about these attacks and how to overcome these attacks is good to know, because this is like in the present context. So let's go to what is an eavesdropping attack. So eavesdropping attacks refers to an attacker who is passively listening to on-chip communication in an attempt to steal sensitive information. So the intention of this attacker is to leak information over a long period of time without being detected. So the recent occurrences of hardware security breaches were hard to detect hardware components that were not a part of the original design integrated to the original design. Leak information have attracted more attention to eavesdropping attacks. So it's as I mentioned you before, like S is sending a message to D. So in the middle, X intercept this message and it is sending that message to Y, and from Y it can go to anywhere else, like beyond this network on chip environment as well. So that's what's happening inside a system in eavesdropping attack. So there are like different categories in eavesdropping attack, as I mentioned to you all. The first one is like malicious routers and colluding applications. So a common threat model that I can explain you is that whereas there's a malicious network on chip IP that colludes with an accompanying malicious application running on another IP to launch an eavesdropping attack. So the malicious IP is X and the malicious application is running on Y. So if you can see, like there are like 2 trusted applications running in the nodes S and D, and they are communicating with each other on a path that goes through the node X. So the hardware Trojan inserted in the network on chip intellectual property during design time 2x, and because of that the router in the X node is infected. So I explained this to you before as well. So the infected router, what it does is like it copies the packet and passes through it and sends them to the IP running on the malicious application at the node Y. And as a result, the malicious application at Y gets the eavesdropping, it gets the eavesdrop on the communication between S and D. So when these attacks are happening, like they have not like altered the communication that had happened. Like even S or D does not know that their communication was intercepted from X. So it is like really hard to detect these types of attacks. So the second type is the malicious network interface and colliding application. So I have given you an idea about what is a network interface to you before. It's more likely if I have to explain you again, like from the intellectual property course, we get a message, and that message is then converted into a packet, and that packet is converted into flits. So that's what happens in the inside of a network interface, and then it feeds the flits to the router. So I just gave you an example about what a network interface is. So similar to a malicious router and an application colluding to launch an attack, a Trojan infected network interface, and it can work together with an application to launch an attack as well. So that's what happens in a network interface as well as in a malicious application. So in this threat model, what happens is like the hardware Trojan is like embedded in the network interface, and it can tamper the flits itself. Like the network interface can like say like the flits going from 1 to 7 to go to from 1 to 9. So it can override the flits and change where it is going. So this is like basically done by modifying the header file of the feed. So because we are not altering data. So those were like the two instances that we can have eavesdropping attack, and there's another way that we can have an eavesdropping attack, which is through external inputs and outputs. So it is like without altering this communication inside the network on chip, the hardware Trojans can directly eavesdrop on the network on chip communication without relying on these rerouting duplicated packets and accompanying application. So this can be facilitated by like having like different input output pins attached to the network on chip. But since the network on chip are resistant to like different like input outputs, as this is not following the bus-based architecture, it's not commonly found. So basically eavesdropping happens via packet duplications or packet rerouting. So those are the ways that eavesdropping happens. So the second way attack is the spoofing attack. So system on chips like rely on the integrity of the data communicated through the network on chip for correct execution of tasks. So if you, for an example, like if you think like if a malicious agent corrupts data intentionally, and that can lead to like erroneous execution of programs as well as maybe like system failures as well. So on the other hand, like if we consider the spoofing is an act of disguising as a communication from an unknown source being from a known trusted source. So there's like a malicious agent which is pretended to be a trusted source that can inject new packets to the network causing system to malfunction. So that's like pretty much about spoofing. So spoofing can be like used to bypass memory access protection by impersonating a code that has permission to read from or write from it. So it's like prohibited. There are like prohibited regions to steal sensitive information or disrupt execution. Or spoofing may be used to leverage and respond to legitimate requests with wrong information to cause system failure as well. So basically, spoofing can be achieved by an attacker replacing the source address of a packet by an address of a trusted type. So this is what happens. So we are pretty much familiar with the term hacking. So this is pretty much what we say as hacking as well. So here I have given you an example. We all think in the background hacking is inside the system on chip, as the RAM and the Wi-Fi is happening. The Wi-Fi module is the one which inputs the passwords into the system, and by accessing the Wi-Fi module through an untrusted intellectual property inside the system on chip, can get the Wi-Fi passwords for itself. So this is about an implementation in the simple IoT system, how a spoofing attack can be done. So it is more likely that we cannot actually detect it because this is implemented in the transistor levels in the system on chips. And as I said, maybe these cases are found by the attacks that are happening in the system on chips, and then most cases we are getting to know that this can happen inside the system on chip. So that's a small example about how this can affect us in the real life scenario. So what you need to get is this detection of these attacks is not as easy as that we think, because from the background it seems easy, but it actually does not. So the third one is the denial of service attacks, which is about the there are three different threats models that we can explain. One is flooding, the other one is packet corruption, the third one is the traffic flow manipulation. So I'll give you a brief introduction about denial of service attacks, because in the next webinar we're gonna discuss about denial of service attacks in depth, because we are gonna discuss about how to detect the denial of service attacks in network on chip based system on chip. So denial of service attack is a network is an attack that prevents legitimate users from accessing services and information from the system itself. So the most common example that I'll be able to give you guys is there's an attacker flooding the network with information that are not needed. So when for an example, when a user is trying to access a website, the request is sent to the web server to view the page. So a server has a certain bandwidth, and that can only serve a limited number of requests at one time. So if an attacker overloads the server with requests, so it will not be able to process the legitimate request of the user. So this is simply a denial of service attack in computer network environment. So I think if you're interested, you can simulate a denial of service attack using JUnit. So if you're interested, you can in your free time implement denial of service attack using JUnit, using a web page, maybe web page that you have created as well. So in terms of the network on chip environment, there are several threat models implemented there, as I mentioned you here: flooding, packet corruption, and traffic manipulation. And the denial of service attacks can have different effects in the system based on the threat model, like performance degradation, quality of service degradation, real-time violations, and ultimately reduction of battery lifetime, because it keeps running and running and running and running without actually use of it. So I'll explain what is a flooding type of denial of service attacks and what is packet corruption, as well as what is traffic flow manipulation to you guys. So uh, in terms of like flooding type of denial of service attacks can happen from malicious intellectual properties, manipulating the availability of on-chip communication resources by flooding the network on chip with packets. So for an example, if you can see in this image, let's say like the blue color one is intellectual property that is creating a denial of service attack. No, sorry. So the orange color one is creating a denial of service attacks, and it is targeting the blue color intellectual property. So it keeps sending messages without a reason for the blue color network intellectual property, and the traffic rate around the blue color intellectual property keep increasing and increasing. And if you want to like pass a message that is important for the application execution from like different intellectual property from to the blue color intellectual property, it might not pass at the time that we want it to pass, because the orange color intellectual property is passing unimportant messages without a reason. So that is the flooding type of denial of service attack. Uh, as well, like in terms of packet corruption, continuous corruption of packets can also lead to like denial of service attacks. Like if we like use hardware trojans to like tamper the fleets that are arriving from a router, it causes like performance degradation, because like if we tamper the fits, what happens is like it is identified as a corrupted fit. So then there'll be like retransmissions and response delays that are happening, and the number of retransmission might increase by time. And again, like what retransmission also do is like the increase the traffic rate within a system. So when the retransmission increases, there can be like deadline violations and performance degradations as well. So there are like several hardware trojans that we can consider when it comes to uh, retransmission. So I haven't actually included it in the slide deck. One is like the quant trojan, the other one is the address trojan, the third one is the head hardware trojan, and the fourth one is the tail hardware trojan. So these are like the four types of trojans that can happen inside a network on chip environment and cause packet corruption. So if you did not like get those names, I'll explain. I'll Please let me know. I'll share with you. So the third type of denial of service threat model is like the traffic flow manipulation. This is like a threat model whereas packets are unfairly treated at the routers to cause denial of service attacks. Like the malicious network on chip intellectual property, once integrated in the system on chip, picks a victim that is like important for the system on chip components and manipulates the traffic flow to, or maybe like for the victim as well. So it is like denying fair access to the allocator and arbiter units in the router. So if we consider as an example, so let us consider CPU inside a system on chip, which is like really important for the performance and the tasks that are carried out in the system on chip. So if we have an IP targeting the CPU, like if we consider the blue color IP here is the CPU, and the orange color one is the uh, hardware trojan implemented IP. So sending messages to uh, CPU directly, which are not important messages, cause like uh, um, denies the access to the other IPs to communicate with the CPU. Like maybe even the memory or the GPU might not be able to communicate with the CPU, because there's a traffic flow manipulation done by a hardware trojan infected intellectual property. So these are like the examples about denial of service attack. So what you have to think if you remember denial of service attack is, there are like different scenarios and different methods, but what ultimately happens in a denial of service attack is somehow the traffic rate inside the network on chip is increased. So it's all about the traffic rate in denial of service attack. So the next one is the buffer overflow attack. So the goal of a buffer overflow attack is to alter the function of a privileged program so that the attacker can gain access and execute his own code. So maybe like a program with high level privileges typically become the target of a buffer overflow attack. So to maybe like to accomplish a buffer overflow attack, the adversary has to insert malicious code and make the program execute the code itself. So the code injection is maybe like the first step if you want to execute a buffer overflow attack. So I mentioned you about the stacks with regard to buffer overflow attack. So out of the models that we can have buffer overflow attacks, one is smashing the stack, the other one is the untrusted IP access. So smashing the stack means like like it is like very common in computer network domain as well. So it is like injecting malicious code and getting it to execute and launch a buffer overflow attack. So it's like a malicious IP has the ability to write on the stack itself and modify the functionality that is happening inside the network on chip. So that's why like this is called the smashing the stack attack, because it gets rid of the currently running application execution and execute a completely different application itself to introduce a buffer overflow attack to the system. So the second one is the untrusted IP, accessing secure IPs. So it is like if you consider there are like some intellectual properties on the system on chip which might contain confidential information, and there are like some untrusted intellectual properties which can potentially carry hardware trojans as well. So the information inside the secure intellectual property code should be protected from non-secure intellectual properties code. That's obvious, right? So since all these IP cores are integrated into the same network on chip, the non-secure IP cores can communicate with the secure cores, and the non-secure IP cores can try to install trojans in the secure IP cores as well. It is like to extract information. So these confidential information in the registers in the secure cores, such as the cryptographic keys, configuration registrations, register information, as well as the secure data, can be compromised in such an attack as well. So this is a threat model of non-secure IP cores trying to access secure IP cores as well. So you might like think like this might be like similar to spoofing attack as well. So there are like similarities when it comes to the implementation of these attacks. So the next attack that I have to discuss is the side channel attack. So before like moving into that, so what you see is like the buffer overflow attack is like we are having code implemented in one intellectual property, and we are altering the application execution within a system. So maybe like a spoofing attack might not be detected, but a buffer overflow attack can be detected because it alters the application execution. And these are like mechanisms that someone can like attack a system and maybe like get the passwords inside the system, get credentials, and like these are like can be implemented in the sensitive environments where like the important information are carried out from these environments. So you understand that detection procedures are important in terms of these as well. So the last and the final type of attack is the side channel attack. So if I have to give a brief introduction about side channel attacks, it's more likely in the earlier days, the attacks on the encrypted devices were based on like observing the ciphertext knowing like both plain text and the ciphertext, and or selecting the plain text to encrypt the results of the encryption. So you might be heard of like Enigma machine, and like in the maybe like World War One and World War Two, it's all about encrypting and decrypting ciphertext to secure information as well as to uh, get information as well. So in contrast to the encryptions that are done there, side channel attacks are attacks that exploit non-functional behavior such as time, power, electromagnetic radiation, heat, and acoustic waveforms to attack a secure system. So the switching behavior, I think like you know about the CMOS semiconductors. So the switching behavior of CMOS transistors can be analyzed to infer the underlying circuit functionality. So therefore, like flawless implementation of a security mechanism can be also vulnerable against a side channel attack. So it's about, like as I said before, about the electromagnetic radiation, heat, and power as well as time as well. So uh, in side channel attacks, uh, in the real case scenarios, like there are like more constraints imposed on systems, such as for performance and power as well. So the even for like systems with theoretically proven for security bounds might have like side channel attacks embedded there, because of when it is functioning in the physical environment, the theoretical constraint might not stand there. So one way of implementing a side channel attack is a timing side channel attack. As I mentioned you that timing can be an way that we can implement a side channel attack. So due to like the computation requirements, secure system often take different times to perform different operations, but by carefully measuring these time differences, like it is possible to extract secret information from a vulnerable system. So this is basically about like it's not going into what are the data that are transferred and how are the data that are transferred. It's like if some set of data is taking 5 minutes to transfer and another set of data is taking 2 minutes to transfer, they like infer like in the 2 minutes these are the set of data that is transferred and these are the set of data that is transferred in like in the 5 minutes. So based on that they can come into conclusions like this is the time the important information is transferred, and this is the time that we should extract this data from the system. So it's like based on the non-functional requirements, they are considering when and where to attack for the system as well. So I think like I pretty much covered all the types of attack that can happen within a system on chip. So I believe like you got an idea about what are the attacks. So if I am to like brief you about the attacks that we talked about today, one is eavesdropping attack, the other one is spoofing attack. So if I'm to explain again, like eavesdropping attack is like listening to confidential information passed through a network on chip when two other intellectual properties are communicating. One listens to them and passes it to someone else. So the spoofing or data integrity attack is like impersonation. So the denial of service attack is like increasing the traffic rate. Buffer overflow or memory extraction attack is like rewriting the applications or the execution codes within a network on chip environment. And side channel attack is like based on the non-functional requirements like time, maybe temperature, and also include time, temperature, as well as like maybe electromagnetic radiation as well. So there are like different scenarios like we can have these set of attacks. Like as you can see, the implementation of these attacks are different from each other, and when we consider again like a system with more than 100 or 200 different components inside, then we have no idea about how these components are designed, because we know about the implementation as well. So the thing is, these attacks can cause serious consequences for the system. So I think like you got an idea about the attacks now. So the next time we'll meet, I'll be discussing about how we can detect these attacks. So the detection strategies can go from like simple statistical methods, like how many messages are passed between time interval, maybe like what are the messages are passed, and there are like several techniques that we can consider about. So if you've been to like the previous two webinars and this webinar, so you might be considering like, is this important for you to learn about these things, like because you might have not met about the this before as well. But what I have to tell you is like, uh, you can understand from the information and the explanations that I gave about the attacks. There are like multiple ways that these attacks can happen. So the detection strategies of these attacks are open research problems that are happening in the world, like because the complexity of the network on chip is also changing, technologies used in the network on chip is also changing. Like there are like for an example, there are like strategies to detect these attacks in electrical network on chip, but there might not be strategies to detect these attacks in optical network on chip or like wireless network on chip. So those are like pretty much open research problems in the area. Like, so if you are interested in like researchers and coming up with your own method to detect these attacks, like these are pretty much open. So there are instances that these attacks have been identified in the computer network environment, but they have not identified in the network on chip environment. So but what someone can easily do is like uh, have an idea about how it is implemented in the computer network environment, and he or she can like mimic how we can implement these detection strategies in the computer network on chip environment. So I think like you got the point about knowing about these things, because it's more about like again to explain that the detection strategies of these attacks in the network on chip environment is critical, and these are all open research problems for uh, researchers to explore. And knowing about these things at an age where you are just an undergraduate gives you the head start for you guys to know about these things and explore more. When you are like, if you are like have an interest to go for a research, you know about these things, and because you are like keeping in touch with these. So that's like basically what I wanted to cover today, so you get a grasp about what we are discussing. So we came a long way from getting to know what is a network on chip, and before we got to know about what a system on chip. So you know that like system on chips are there in like almost every IoT device now. So uh, if you are an maybe like if you are an I student or maybe CSC student, it doesn't matter actually. So for I students, they're like familiar with the IoT devices as well. So they might be interested in the designing the IoT devices and designing the system on chip. So when like for I students, it's more about like when they're like designing these systems, they can like concern about these attacks. And for CSC students, even though like sorry, for CSC students, it's more like even though like if you are not pretty much know how to implement the system on chips in a use case, but you know that these are the things that can happen inside a system on chip, and there are like several vulnerabilities that can happen. So you can have that knowledge, and then like you can maybe use a statistical method or maybe machine learning or maybe a different approach to detect these attacks. So these are like not limited to a certain set of students, because this is everything about this is about computer science. So these are like open research problems in the world at the moment, and these are like explored at the very moment that we are discussing it now, and they are like pretty much going to be a major concern as the world is moving toward the fourth industrial revolution, as the number of IoT devices that are in the world are increasing and increasing, and as these IoT devices are increasing, the number of attackers are also increasing, and the number of types of attacks are also increasing. So pretty much these are open research problems, and I believe that you will be there for the next webinar as well. So I can give you an idea about what are the detection strategies here, about how to detect these attacks, and like they are like really interesting because we can go deep down into the hardware implementation level and know about how these attacks are happening, as we discussed today. So now we have a clear idea about how these are happening in the hardware level, and how the messages are being passed and how they are collecting information. So now you know how these attacks are implemented. So in the next webinar we'll be able to tackle how to detect these. And again, before the end, I'd like to let you know that these are open research problems. So if you are keen on doing a research, or maybe like want to explore something and want to do your own innovation about how to detect these attacks and want to come up with your own method, uh, this is a really good area that you can consider for doing a research. So that's pretty much it from my end. So if you're interested, you can look into like this, like there are like several research papers that are there as well. So thank you very much.
Thank you, Chamika, for conducting this valuable session. And guys, there is a small feedback form. The link is in the chat. So guys, please take a few minutes and fill this form. So this is the end of today's session. Let's meet on the next day. Thank you and goodbye.